Okay, welcome everybody. The idea of this series of short talks interspersed with code is to give new graduate students and even some undergraduates who will be working on Atlas projects a bit of motivation behind the code that you're going to be running, so you're not just running things, getting results and not really understanding what's behind them. I will say that these talks are not meant to be completely in-depth. You know, it's assuming that you will go and do some of your own reading around some of these items and assume some background knowledge, but it will also be a good opportunity for any questions that will come up that you can then ask me or any Atlas faculty members, and we'd be happy to answer. So in the first of these talks, it's just going to serve as an introduction to the Atlas detector at CERN and the Large Hadron Collider in general, and then you'll be going to run some code following this, and then I'll meet you back here afterwards. So let's start. We are of course here talking about the Large Hadron Collider at CERN in Geneva, Switzerland. The Large Hadron Collider is 27 kilometers in circumference and collides protons at very close to the speed of light. We work on one of the experiments in particular called the Atlas detector, which I'll be talking a little bit about behind me here. We're going to go into how, as experimentalists, we then start to analyze some of this data. So the LHC provides proton-proton collisions. This is a very crude picture of the Atlas detector, which is a huge barrel, essentially, that is around 40 meters in length and 25 meters in diameter. So if you've ever been to Paris, it's about as big as Notre Dame. And it weighs over 7,000 tons, which is as much as the Eiffel Tower. So it's as much as an engineering feat as it is a physics feat that we can use it. And it still amazes me that, you know, all of the components are within micrometer precision of each other for all of this to work. So this is the Atlas detector that we're dealing with, and the LHC shoots protons down the beamline in both directions of this 27 kilometer circumference ring I was telling you about, and we collide them as close to the center of the detector as we can. The LHC doesn't just launch single protons around, we have bunches of almost 10 to the 10 protons, so you can imagine bunches of these protons going in either direction and colliding together. And if you just put one bunch in and collided and then started up again, getting them very close to the speed of light, it would take a very long time. So actually these bunches of protons are spaced out into very small bunches which are around 25 nanoseconds apart from each other. So we have a collision every 25 nanoseconds, which leads to over 40 million collisions per second happening at the LHC, which is just an incredible amount. It's such a high amount that we can't actually write that many events to disk. Okay, we just physically, the hard drive's head can't move fast enough to write all of this information. So we have to employ something called triggering, which you can go and look up more about. But the idea of triggering is essentially to look at what comes out of these collisions and try to identify interesting events that might teach us more about the standard model of particle physics, or may even be new particles that we've created, and try to only write those interesting events to disk. So that triggering allows us to go from 40 million collisions per second to around 1,000 events per second that we can actually write to disk. And those 1,000 events that are written to disk, we as experimentalists then can use and write computer code to analyze those events and try and reconstruct what happened in these collisions. So if we go over to this diagram on my left here, this is, I've got a bit colorful here, a bit more of a cutaway of the Atlas detector. So if this is the barrel, you're looking down now, the end on in the barrel, so the beam line is going into the picture here, and essentially what you're seeing is that the Atlas detector is built like an onion, essentially, with many different layers. So in the very innermost layer here, you have the tracking detector, the inner detector. Then you have the electromagnetic calorimeter, which is in green around the outside, and the hadronic calorimeter around that. And then at the most extremes, you have these muon chambers, which have the same kind of technology as the inner part of the detector, but is in multiple chambers around the outside. So why am I showing you this diagram? Well, we have these collisions that happen at the center of the detector, and then just like an explosion, all of the particles that are created in that collision and their decay products will fly out from that collision point. And the way that the Atlas detector is designed is to identify all of the different kind of particles that come out of those collisions. So if, for example, we take a particle, so I'll talk more a bit about this later, but let's say that a quark and an antiquark collide and create a standard model particle called the Z, and that decays to 2 electrons. Well, if that happened in this collision, then we would expect to find 2 electrons in the event. But what does an electron look like? So here we can see that an electron is a charged particle. So for the inner part of the detector, we expect it to leave, it basically ionizes silicon, and if it's going through a gas chamber, ionizes some of the gas, which can then be read out, and we can read that that particle has passed through this part of the detector. We call that a track. And we can lead this track out of the inner detector into the electromagnetic calorimeter, which is designed to be dense enough to stop particles like electrons and photons. And the way it does that is through Bremsstrahlung and some interactions. You see a shower, as we call it, basically a shower of particles, which then stops the electron. So if we see a track leading to a shower in this part of the detector, then we generally think it looks pretty much like an electron. And we can actually then, to tell which direction that electron went in, and also how much energy it had, as we can add up all of these different parts of the shower to figure out how much energy there was in the collision. If you take a photon, for example, which isn't charged, therefore it doesn't ionize the inner part of the detector, so it wouldn't leave a track, but it would still be stopped by this electromagnetic layer of the calorimeter. And so if we see a shower without a track leading to it, then we think that that's a photon. I won't go through these others in detail, but you can have charged hadrons, for example, like a proton, and that is much more massive, so it would punch through the inner detector and the electromagnetic calorimeter, leaving a track behind it because it's charged, but it would then be stopped by the hadronic calorimeter out here in red. So you would see a track going all the way out, and then a shower in the outer part of the detector if you had a charged hadron. And similarly, if you had a neutral hadron, like the neutron, then there wouldn't be a track in the inner detector or the ecal, and it would shower in the hadronic part of the calorimeter. So we have a few other particles left. The muon, for example, is charged and is around 200 times heavier than the electron. So it would leave a track, but because it's more massive, it would keep going all throughout the detector. And that's what these muon chambers, the muon spectrometer on the outside, is for, because if you see tracks all throughout the detector, including these outermost chambers, then we have an algorithm that fits this track all the way through, and we decide that that's a muon. And actually from the curvature of this track, because the whole thing's in a magnetic field, we can work out the energy that that muon had. And lastly, if you had a neutrino, well, neutrinos very rarely interact at all, so actually we wouldn't see the sign of the neutrino at all. But if there was an event where we suspected that there was a neutrino in it, you would see some missing energy in the event. If you added up all of the other components, you expect the event to basically cancel out in the momentum. So if you have any leftover momentum, it looks like there's some missing on this side, then we infer that a neutrino was there. Okay, so this is how we use the Atlas detector to identify the different products that come from our collisions. And we use computer code essentially to do this. Algorithms identify all these different objects and store them in objects we call events. So a single collision is a single event, and it may have a number of electrons in it, or muons, or neutrinos, or these objects, we can't generally tell exactly what hadron it is, so we define these as jets. Those are stored within the event for us then to write computer algorithms to select events. So, for example, if I was looking for the standard model Z decaying to 2 electrons, I would take the data set that we had collected and I would tell the computer program, only give me events that have 2 electrons in it. And therefore I'd get a subset which had none of these other objects, but just all events that had at least 2 electrons in it, and I could then do my analysis. Okay, so I've told you a little bit now about how the Atlas detector sees these collisions and how we can interact with them. One question that you might ask is, if it's a proton-proton collider and protons are made of 2 up quarks and a down quark, then how can we have a quark-anti-quark annihilation to create a Z particle, for example. And there are other types of interactions, but just for example, this is a very common one. And the reality is that inside the proton, we don't just have these valence quarks, the quarks that make up the particle. We really have a soup or a sea of particles and antiparticles being created, splitting from gluons backwards and forwards all of the time. And we're at such high energies that actually the probability of you interacting with one of these other particles, a U bar for example, or a D bar, or even a strange quark and so forth, actually becomes non-negligible. So we can actually have these QQ bar collisions, annihilations many times. Okay, so of the two protons colliding, this is a Feynman diagram, which you may or may not have seen before, and it's just telling us that we're having a quark and an anti-quark colliding. So this is meant to represent time along the x-axis and space along the y-axis. So we have a QQ bar annihilating, and in this case creating a Z boson, which then later decays into an E plus, E minus. So this is a part of the standard model of particle physics. I will actually link to another video where we will go into some of the limitations of the standard model, which is basically our current understanding of the fundamental forces and particles of nature along with their interactions. So you can go and watch that video for more information about also some of the new particles that we're looking for, which will help hopefully understand some of the deficiencies in the standard model. So I'll leave that video for you to go and watch for more information there. And the next part that you'll go on to in the coding now is that, as well as collecting data, what we do at the LHC is compare our simulations of what the standard model should look like and what these new particles could look like if they were created. We compare that simulation to the data to know if we've discovered a new particle or not. And so the first coding project that you're going to do now is actually to generate some of these processes. So here, in fact, we're going to generate a signal, which you'll learn more about in the other video, but you're going to generate a QQ bar process creating a new particle, a very heavy particle called the Z prime, which would decay to 2 electrons. And you're going to learn about how we produce that simulation. Then you'll come back here for a quick recap and looking at what you'll do next, and then you'll actually start to analyze those events and try and reconstruct what that Z prime would look like. So thank you for joining for the first part of the video, and we'll see you back here after the coding project.